In this session, we'll be talking about quantum gate implementation and in the Universal Quantum Gate Library. So there are some basic gates with which we implement all the other gates in the circuit. So we'll be talking about that and the mathematics behind it. So let me share my screen now. Okay, so right. So let's start with the definitions of basic terms here. So in the quantum, when we talk about quantum states, like in classical states are very straightforward. We have n bits, then like we have 2 power n states possible, but at the time simultaneously only one state is there. So in quantum, the level of parallelism is huge. So we can have 2 power n number of different quantum states simultaneously. So to model that mathematically, we in a circuit we have inputs and outputs, right? Just like in classical, we move from left to right, the inputs and some transformations or gates, and then at the right side we have the outputs. So mathematically, we represent the inputs as column vectors and the outputs as row vectors. So in any quantum algorithm or function, the of course the states are being processed. So this processing is more than mere flipping of states. Like in classical, zeros turn into one and one into zeros, so that's just mere flipping, right? So here we rather call them as evolutions, and mathematically these are nothing but some operations on those column vectors. And any physical system that can be you know uh, that can implement this kind of operation, we can call them as quantum gate. So that depends on our low level technology that we are using. So in ion traps, it's RF, and in photonics, it's lasers, the mirrors, and phase shifters, like that. So this is just a like a small pictorial representation. You have many quantum bits, qubits, and you apply some kind of, like, it's not even like it's not particular to this. So it depends on the technology, right? So you apply some kind of transformation physically, such that it in this case it transforms its spin or the phase. So that we can call it as a quantum gate. So in terms of mathematics, these are basically just square matrices, unitary matrices, and like we'll see about that in detail here. So like as I told, the inputs are represented as column vectors, right? So in the first case, the zero over here, that should be seen as input, and in the second case, this, that should be seen as the output. Uh, and if you have multiple qubits, then the combination, like 00, 01, 1011, these are the combinations possible. So this is just like basic representation of them in mathematics. So this will be very useful going forward, because all the algorithms are basically all manipulation of the states using mathematics. So, and any gate will can be represented as this, basically the span of the vectors, input dot output. So in case of NOT gate, if we see, if we have this as input, 1 0 column, and the corresponding output would be 0 1, because 1 will be converted into 0 and 0 would be converted into 1. And in the next case, we have 0 1 as input, and in that case 0 would be converted into 1 and 1 to 0. So mathematically, this is how we derive with the I mean, we come up with the representation of gates as matrices. So now, as for an OR gate, we have 0 1 1 0 as the matrix. So this is the most basic reversible gate that is there. And in a circuit, of course, multiple gates will be there. In that case, we represent it mathematically as a combination of matrices, as in we multiply them, and the order of combination would be like for example, let me try to annotate here. So y is equal to some uh, function of x. So this function would be a combination of gates. It could be u3 into u2 into u1. So this means that x is first operated using the operation u1, and then it goes to and then u2 operation is applied onto it, and then u3. So finally it would be represented as u3 into u2 into u1 of x. So x would be the initial input state and y would be our final state. So in quantum, the bits can be entangled within themselves. So in those cases, the corresponding superposition would be found in the output states also. So it's not like every bit is independent of each other. So that depends on the coupling graph that we have, and so the superposition depends on our system. So that is mathematically also uh, carried forward, this entanglement. Just a minute. Okay, I'll move forward. So in designing the circuit, so there are multiple libraries that we can use, as in libraries, as in just that the combination of gates that we want to use, because of course all sorts of gates are possible, but in our target hardware we cannot expect to have all the gates. Like, of course that's really great to have them, but practically speaking we'll probably have just a few set of gates, and using those gates as universal gates we can span up into any quantum circuit that is there. So like in classical, NAND gates can be used to form any other gate, right? So they are the universal gates. I mean, they're one of the universal gates in classical domain. Like that in quantum we have any one cross one, as in one cross one unitary operation, and two cross two unitary operation can be used as the universal set of gates. So we can have that as V gates and C naught gates, or Hadamard gates and C naught gates, like that. So the basic representation is shown over here. So this will be like useful when we see any quantum circuit further. So basic representation, especially in this case of C naught, is that the dot represented is the control bit. So here the bit A is controlling the bit B. So the bit B is known as the target bit. And here, whenever A is high, I mean, whenever A is 1, only then the bit B is being flipped. So if you see the truth table for this, it's basically just a XOR truth table. But the physical meaning of this is that the bit A, if it is 0, then we don't touch the bit B. If bit A is 1, then bit B is being flipped. So in a previous session, like the physical implementation, one of the physical implementation of this was explained using photonics. Okay, so and these gates are like basically 3 cross 3 matrix gates. So here 3 qubits are being used and processed. So like multiple uh, what do you say, like multiple combinations of processing are being used. Like just like if you have 2 qubits, then in classical domain, if you have 2 bits, then in classical domain you have and, or, NAND, NOR, XOR, right? So they are multiple combinations. So similarly in 3 cross 3, these are the multiple combinations there. So like in Toffoli gate, what basically happens is the third bit, so these are 3 qubit gates, right? So the third bit is the target bit, and the first 2 bits are the control bits. So like it is flipped only when the all the control bits are on, otherwise it is not flipped, and the first 2 bits are not touched. And in swap gate, unconditionally it just swaps the 2 qubits. That's like straightforward. And the Fredkin gate is the you could see the like superset of swap gate. It basically uh, is a controlled swap gate. So using a control bit, it swaps the 2 other bits, and if the control bit is low, then it does not swap. And the pairs gate is like a combination of C naught and Toffoli gate, and like it, so it remains idle when the control bit is 0, and if it's 1, then if the control, there are 2 control bits. So if the first control bit is 1, then the second control bit is flipped, and if the second control bit is also 1, then the third control bit is flipped. So like these are just some basic operations and commonly used gates. So only when we have an algorithm in mind and when we want to convert them into the circuits, then depending on the operations that we do mathematically, depending on that we can choose from any of these gates, or we can even have any other gate of our own choice and then try to implement it on the hardware. But I've just listed them because these are like the usually commonly used gates. So for any circuit design, we have this metric quantum cost. So actually, in the literature, I saw two um, like differing notions of this quantum cost, but mainly it is just that when we have any circuit, the number of gates that we use is being showed by the quantum cost. So then, to be precise, the number of 2 cross 2 gates. So even these Toffoli gates and Fredkin gates, 3 cross 3 gates, these are being converted to 2 cross 2 in like behind the scenes. And the number of 2 cross 2 gates and the number of 1 cross 1 gates, they are basically uh, called as quantum cost. So before moving forward, I just want to like touch upon this other gate, V gate. So this actually, I was surprised by the name of this, but this is nothing but simply mathematics. So for any matrix, you have a square root of the matrix, right? Given by this formula. So similarly, for a NOT gate also, if you NOT gate is just a 2 cross 2 matrix. So if you take the square root of it, you get this V gate. So this is used because like in most applications, you don't directly use NOT gate, you use controlled NOT gates, or conditional, I should say. So there, you can rather use this V gate, and you can apply two V gates, or V transpose. So what happens is, so you can have two V gates with different control bits. So depending on the control bits, it will either be a NOT gate or it will be an identity gate. That is basically not touching it at all. So like we'll see that in a implementation. So if you talk about Toffoli gate implementation, so as I told, the first two bits are control bits and they are not being touched. And the second bit is basically where we basically do this or of it. So in the implementation of it, uh, like if you want to understand it, you can just take basic zeros and one states. So if you have like A and B as 0, and the output R should be zeros or C, that is basically C itself. So basically nothing should uh, happen, right? So V gate here and the V transpose gate here have the control bits over here. So basically what happens is, if the A bit is 1, then V gate is being applied. If the A bit is not 1, then V gate is not applied. So I know I'm talking in a very digital sense here, but basically what happens is, mathematically, when you open it up, like when you write it down mathematically, so whenever the superposition part is 0, then you do not apply the V gate, and whenever the superposition part is 1 with whatever probability, then the V gate is applied. So the probability is carried forward in that manner. So just to understand this, we can see it in a very digital sense. You can see it as 0 0 0 1s and try to understand, or at least just like verify the outputs. uh, yeah. So if you have 1 and 1 in A and B, then what happens is, the V gate is, first of all, the first V gate is applied to C because A is 1. The second V gate is again applied to C because B is also 1, right? And the third gate is not applied because after, like you can see this operation, right? C naught operation. So the A is being XORed with B. So the A is basically being flipped, and since B is also 1, so A or B is 0. So when this is 0 now, so the V transpose gate is not applied. Just V and V are applied. So basically, what happens is, when two V's are applied, V, since it is the square root of naught, so basically C is being flipped. So it acts like a uh, inverter, not gate. and let's try to verify it from the output also. R is A dot B and XOR C, right? So A and B are 1, so C is being XORed with 1. So whenever you XOR anything with 1, you are basically applying a NOT gate, you're flipping it. So there are mathematics sits right here, or you could say the circuit design sits right. And like similarly Pierce gate is right. I mean, I don't think I need to like go into the details exactly, but yeah, you get the point, right? Or if you want, like I can go through it. All right. All right, so like coming to the end of it, I just wanted to have a small operator or a function that we are familiar with, the half adder, the most basic one. So this is simply being done with two gates, Toffoli and C0 gate, and the Toffoli is also again broken down into the smaller gates. But yeah, so this could be broken down as smaller gates. That's what I meant. So the quantum cost of this whole half adder circuit would be, for a CNOT gate the cost would be 2, and for a Toffoli gate it will be 5. So the whole quantum cost here would be 7. So right. So like I just want to end this session with this, but if you have any questions or if you're not understanding the circuit part, I can go through this. So do you want to ask anything about this? Hello.
Huh.
Right.
Mm. All right, guys, any questions? If not, we'll move on to the next.
I know I might have rushed, but the basic concept is same. And if you want me to go through the any of the circuit in detail, or if you not understand the Toffoli gate in detail, then I can go through it again.
Hmm. It's okay.
Okay.
We'll send the recordings as well. So yes,
We have a question. We have a question.
on chat.
Explain Toffoli gate.
Okay. Uh, right. So forget all this quantum. Toffoli gate is essentially just a reversible gate, and it works with 3 bits or 3 qubits. However, so the mathematics still remains the same whether you take bits, zeros and one, or qubits, complex numbers. So uh, Toffoli gate is just the name given to this gate, where the operation is this: the first 2 bits are not touched, the third bit is being operated as such. So basically, it is being XORed or flipped based on the first 2 bits. Uh, Flipped as in not. So it is Toffoli gate is like a superset of C not gate, you should say, um, right? And wait. So how else can I put this? Mm, okay, fine. And let me go into the implementation on 2x2 gates. So in the first case, let's have zeros and zeros in A and B. So what we expect our output to be is 0 XOR C, right? So that is C itself. So we want to have the C bit untouched. So basically, this is again even in the high level description of Toffoli gate, this is the concept, right? When the two target bits are 0, then we don't touch the sorry, when the control bits are 0, A and B, then we don't touch the target bit. When the two control bits are high, then we flip the target bit, basically inverted. So here the formula sits right. So let's look at the implementation. Uh, this is a V gate, and this is a V gate, and this is the V transpose gate. So the first V gate is not applied to C because it is being controlled by A. So this is the notation that we use when we basically like even in the control C not gate that I showed you a little earlier, I mean control not gate. Okay, where is it? Yeah. So even in the control not gate, the dotted signal, the dotted bit qubit is A, and the XOR qubit is B. So what it means is the target bit B is flipped depending on the control bit A, right? Similarly, if you see the target bit C is acted upon by the V gate depending on the control bit A. So when the control bit A is 0, then we don't have any, it essentially like it is, the gate is not there at all. That's what it means. So if you want to understand this physically, then you can think of two electrons and with some spins, and the electron spin can be inverted by act by like putting some microwave frequency, or the electron spins will be affected, like there will be some particular frequency. When we blast that wave, then the spin would be inverted, right? But then this frequency would be affected by the surroundings also, so it's not completely isolated. So when there are two electrons with different spins, the target electron, its frequency would be, I mean the frequency required to change its spin would be affected by the spin of the surrounding electron. So here the surrounding electron is the control bit, and the target electron is the target bit, right? So like that you can understand it physically. So coming back to the circuit, so A was 0 and B was 0. So because of that, this V gate is not applied, and again this V gate is again not applied, right? So when B is 0, and this means it is a C naught gate. So when B is 0, again, according to the C naught gate, A is again not touched. So again, this is still remaining 0, and this is also not applied. So which means the C is intact. So that's what we wanted over here, right? And let's go with 1 1 now. So 1 1 according to this is 1 XOR C, which means C naught. So we want to flip this bit, right? So let's see, this V gate is applied definitely, because this is 1, and this V gate is again applied because this B is 1, and this V transpose gate depends on the value over here. So here A bit is being controlled by B bit, and since B is 1, so A is flipped. So here A becomes 0, and that's why this V transpose gate is not applied. So basically V gate being applied twice is basically a NOT gate. That's why I went through the V gate mathematics. So it's just the mathematics, and like applying the V gate twice, we get a NOT gate, and we have C naught over here, right? So let's just go through one more thing. Like just take 1 and 0. So again, 1 and 0, A dot B is becomes 0, and 0 XOR C is again C. So we don't want to touch it, right? So V gate is applied, and because it's 1 here, 1, and here it is 0. So this V gate is not applied, and since B is 0, A is untouched. So here it is still 1. So V transpose gate is applied. And again, with the mathematics, V and V transpose, when we apply them together, so they become an identity matrix. That's the, I mean, that goes by the definition. The physical implementation, that we don't need to worry about. I'm talking about the mathematics here. So, right. So we have just V gate and V transpose gate. So this becomes an identity matrix. When you what you mean as an identity matrix is basically you're not affecting or processing the bit at all. So it is again intact, untouched. So that would do, right? So is that clear now, or is there something that you something else that you wanted to ask? I'm not able to see the chat actually.
Uh,
I just wanted.
he said it's clear. Thanks.
Okay.
Hmm.
All right. So I'll stop sharing. Nilay, you'll continue.
Yeah.
Okay.
Yeah. Is it visible?
Um, yes.
Yeah.
Yeah. So yeah. Okay. So like Kedhar spoke about the universal gate. So the basic meaning was like suppose you have a cubic 0, cubic 1, and then you have this and you have a swap gate between them. So for us, we put this swap gate into the circuit composer, but when it's implemented on the real quantum hardware level, this swap gate is getting decomposed into the universal gates. Like depending upon like different architectures have the based on different families of universal gates. Suppose if I consider the IBM's one, so IBM's universal gate family is like the Clifford one, which uses the C0 gate, the rotational gate as the universal gate. So suppose if I'm implementing like on the circuit composer, if you put a swap gate between this, for us it will be just a swap gate. When you see on the real hardware level, so you will have Q0, uh, you have Q1. So there will be a C0 gate over here from Q0 to Q1, and then there'll be a C0 gate in the opposite direction from Q1 to Q0, and again there will be a C0 gate from Q0 to Q1. So we draw swap gate on the circuit composer on Qiskit platform, but on the real hardware, swap gates get converted, decomposed into a C0 gate and implemented as this functionality. So if you work out the mathematics, when you take the tensor products of these three gates, the matrix you will get at the end will be nothing but swapping these qubits. So this is basically funda of like the universal gate. So yeah. So as he spoke about so the one. Yeah. So as you can see over here, there are three universal gate families. Again, it depends upon the architecture you want to work upon. So the first one is which has the rotational gates, the C0 gate, and this is the one which IBM uses. Like it's dependent upon the people who are working making the quantum computer to take on which library. So the first one, it's a one qubit gate, and the C0 is universal. So the basic funda is like all the gates they're getting converted using all the gates given in the set of that particular universal gate family. Second one is the Baranko gate. It's a two qubit system which is universal. So all the gates, whichever you implement, they will get converted into like they'll get uh, made up like a functionality will be with the given the gates in that particular set. So this is the basic funda. So and all like in a classical world we have NAND technology, NOT technology. So that is a universal gate family for irreversible circuits because classical computing is like much more irreversible in nature. So we use the NAND technology, the NOT technology, which is universal gate family for the irreversible gates, irreversible circuits. And then you have the Topoli, the Paris, and the Fredkin gate, which Kedar talked about. So they are for the classical computing, and you can say for the even for quantum computing, for the reversible gate, universal gate family. So what universal gate family means is that you can come up like whichever gate operation you do, you can have that gate operation with the set of like with the combinations of the gates in the family set, like the universal family set. So and then you have the quantum computing universal gate family, which is nothing but the C0 and the rotational and the other families which are being mentioned over here. So given yeah So, like we spoke about, like we'll be working and developing the hardware, which is specifically for a particular purpose. So, I guess I should tell about like what factors we need to tackle, like to make a particular application specific. So, this is the flow chart, like where you have the quantum algorithm, the programming, the quantum program, the quantum compiler, the quantum circuit, and the quantum computer. And at the end, you have the results. So that said, blue dotted circle is known as something but called software development kit. So it basically tells like it's the communication medium when you're trying to interact your digital bits into the quantum qubits. So that is the medium through which you interact. So when you're trying to design a particular hardware for a particular algorithm, so the first you need to focus on designing the which quantum compiler, like how do you want to come up with a quantum compiler. Then that quantum compiler, you have the quantum instruction set architecture and the which family, like universal gate family, which you want to adopt. So whichever gate which I'll be using, suppose if I'm using the first family where I have the rotation and the C0 gate. So all the gates like the swap gates and the other all will get implemented using this. So I have to design my instruction set using only these particular gates. But if I use my Berenko universal gate family, then I have to make my own system in a such a way that all the gates will get implemented with the gates which are there in the Berenko family and it's shown on with the next family. So that's just like when you're coming up with the application specific design, you need to choose, like you need to have your own base, like okay, I'll be taking this, then I'll be merging it with this, and then only I'll make something. So we need to decide what you actually want to. So then you have the three major functionalities in quantum compiler is nothing but there's decomposition, which means that you decompose the program into elementary operations. That is gates. That is nothing but your involve you're decomposing each and every gate into the universal gate set library. Like you're trying to make that specific gate using only the universal gate. Then you have the optimization. This is nothing but optimizing the quantum circuit, like the sequence of the gate. So basically, you try to like suppose if I have two signal gates back to back, it won't make a effect to a qubit. So if I have two X gate back to back on a qubit, so that won't make a effect. And if I have two Hadamard gates, so that won't affect the state of the qubit. So you can get along. Like if I have this example, like given on the right hand side, like first I have the swap gate, then I do the decomposition. So decompose after that, the swap gates get implemented. Mm, Yeah. So I have the swap gates. This thing gets implemented using this part. So I have my decomposition right down over there, and I have this being mapped over here. And then I have the optimization. Then I see that these two CNOT gates are back to back and for a 2-qubit system. So it really won't affect the state of both the qubits. So you can get rid of them. So then I just write down this part. So which I have written down over here. So this is called optimization of a particular quantum circuit. So it's there. Like if you apply two similar gates back to back on a particular qubit system, it won't affect the qubit system. So you get rid of them because you really don't want extra gates to be there on your quantum, like where you implement it on your hardware, because that would result in drastic changes in your fidelity and many other parameters. So this is the three main functionalities. And the third one is mapping. So mapping is like actually one of the toughest part, I guess, because you're trying to map something like when you have it all on your computer, like when you have it in a compiler, it's the ideal qubit, like ideal logical qubit which is there. But when you're trying to map it into a physical qubit, you have many constraints because uh, which I'll explain later why it is the toughest part, because you need to see how qubits are connected with each other and there are a lot more parameters. So moving on further. So suppose I have this particular example over here. Uh, it's just a generic quantum circuit it is for 4 qubits. So and I have given a constraint like what I was telling about mapping. So the very first constraint which comes when you try to map is that for us when you put on a simulator, it's like all qubits are connected with each other. But when you're trying to map it down, it's the scenario is not the same, because you can't have a system where all the qubits are connected with each other. That's like something, not a general approach. Like for the time being, I don't think it's possible now, because that would result in a drastic changes in hardware industry. So given the coupling constraints where you have Q1, Q2 connected, Q2, Q3 connected, and Q2, Q4 connected, and Q2, Q4, and Q3 are not connected with each other. So then there's a logical in circuit. We have a logical circuit which we have built on the compiler. Like we have written a code on the compiler, and this thing, when it gets mapped down to the physical circuit, it gets implemented in this particular fashion. So because of the coupling constraint, so you can see there are like quite differences over here coming up. Like you have TX to from 3 to 4, but you have a gate from 2 to 4, and you didn't have swap gate here, you didn't have swap gate here. So these are like differences which you'll notice because when implementing the circuit which we have made on a system, and when it gets mapped down to physical circuit. So why these differences? Yeah. So this was all because of coupling constraint. So this is nothing but the picture of the device image of IBM Q5 10 Array 5 quantum computer. So this is where the qubits are there, like all the 5 qubits are mentioned, and this is the coupling graph, which is there. So each line tells the connectivity between two qubits, and each node, I think, it represents the qubit. So like 0, 1, 2, 3, 4, they represent the qubit, and the edge represents how they're coupled with each other, and like in what fashion. Like we can see, like there's no line between 1 and 4, which means 1 and 4 qubit are not connected with each other, and there's no line between 0 and 3, which means 0 and 3 they're not coupled with each other. So that is the constraint which we have given, but we have to implement. Suppose if we have a circuit which we make, and there is a gate between 1 and 4, but really on your hardware we don't have connection between 1 and 4. So how will that get implemented? So see, given this example, the in logic circuit, there is a CNOT gate between the logical qubit B3 and B4. But when you see the coupling constraint, which is implemented, Q3 and Q4 are not connected with each other. So like it's like B1 is nothing but Q1, B2 is Q2, B3 is Q3, and B4 is Q4. Like you're mapping the logical qubits with the physical qubits out there. So we have a gate between B3 and B4, CNOT gate, but B3 and B4, like Q3 and Q4, are not connected with each other. So that is the query, which is ambiguity, which is being arised over here. So how do you actually do that? So we have a scenario which says that the gate between B3 and B4 will be not executable because the coupling constraint is there, because Q3 and Q4 are not connected. So what we really do is that, but the alternative way is from Q3 to Q2 and then to Q4. So what we do is that we have a logical qubit B3 mapped onto Q3 and logical qubit B2 mapped onto Q2. But we are about to perform the operation between B3 and B4, which is a CNOT operation. So what we do is we put on a swap gate between Q3 and Q2. So basically you try to interchange the states of both the qubits. So your physical qubit Q3 will hold the logical state of B2, and your physical qubit Q2 will hold the logical state of Q3. So you are performing CNOT operation between the logical states of qubit B3 and B4. So you sub down the state. So Q2 holds the state of B3 and Q3 holds the state of B2. And then you can see like there is an operation like Q2 and Q4 are connected directly with each other. So you are performing CNOT operation between the states of B3 and B4, and they're connected now with each other. So then you can perform the CNOT operation. So initially we had CNOT between B3 and B4. Now we swap down the states. We have the B3 on Q2 and B2 on Q3. So just get the difference that B3, B1, B2, B3, B4 are nothing but the ideal logical quantum the qubit states, and like there are like qubit logical like qubits which are there on the compiler side, but and q1, q2, q3, q4 are nothing but the physical qubits which are right down there. So when you're trying to map, initially you map them one on one, then you apply a swap gate because you need a connectivity. You need to perform this tx2 operation, which is between b3 and b4. So you swap the states of the q3 and q2 state, q2 qubit, and now the q3 holds the state b2 and q2 holds the state b3, and you're trying to perform the C0 operation between the states b3 and b4. So they are connected directly now with each other. So then you apply a C0 between Q2 and Q4. Earlier, the C0 was between B3 and B4. But why not between Q2 and B4? Because the state B3 is the control state and the state B4 is the target state. Over here, which qubit holds the control state? That's Q2, which holds now the B3 state, because over here your B3 is nothing but the control state. And over here, Q2, the qubit Q2 is holding your control state B3, and your target state B4 remains the same, which is in the Q4 state, Q4 qubit. So we try to put a C0 from the qubit which holds the control state, that is B3, which is nothing but Q2. So we try to we apply a C0 operation between Q2 and Q4. So you get rid of this like this. You are executed up till now, and then you have CX3, which is nothing but P2 and B3. And given the constraint, your Q2 and Q3 are connected with each other, so you can directly, yeah. So you can implement directly, but the difference we see is that they are interchanged with each other. Like Q B2, like they just flipped because this was in this particular fashion and this is in this now. One sec. Yeah, it's like kind of flipped. The reason for flipping is that you have put a swap gate and have interchanged the states of B2 and B3. So initially, now, initially your Q3 qubit stored the state B3 and Q2 qubit stores the state B2. But after performing this swap operation, you have interchanged the state. So that's why the gate is flipped. And that's just the reason why you have a flip over here with respect to this. And similarly, the RX gate was implemented on the B2 state. And now your B2 state is nothing but with qubit 3. So you have a RX gate over here at 3 qubit, third qubit. And similarly, when you have a fourth, yeah. So when you have, so you have implemented up till over here, and then you have a C04 gate, which is nothing but between B1 and B2. But now your B2 state is with Q3. So, and your Q1 is not directly connected with Q3. Like we can see over here, Q1 is over here and Q3 is over here. So they're not directly connected with each other. And even though the operation is between B2, but the B2 state is now being held by Q3 qubit. So Q1 is not directly connected with Q3. So we need to do something. So that's why we put a swap operation between Q1 and Q2. So your Q1 and Q2 will swap with each other. So then you can see the B1 state, which is because you're trying to put this. Okay, let me erase all. It's getting quite messed up. Yeah. So you're trying focus on this gate. You're trying to apply control not force gate between the state B2, which acts as a control state, and state B1, which acts as a target state. But we have implemented a circuit up till over here, and the current scenario is that your state B2 is being held by qubit Q3 over here, and B1 is again it's held by Q1 itself. So there's no change in Q1, but there is a change in state of B2. So you are trying to apply not between state B1, which is held by Q1, and state B2, which is held by Q3. So technically, you are applying control node between Q1 and Q3, since they're not directly connected with each other. So you put a swap gate between Q1 and Q2. You bring down the state B1 to qubit Q2, and you will swap the B3 state will get swapped to qubit Q1. So after this operation, your Q1 holds the state B3, and your Q2 holds the state B1, and your Q3 is holding B2. So now you have B1 and B2 state connected with each other. So, and then you apply a CNOT operation because your qubit Q2 holds the B1 state and Q3 holds the B2 state, which is given over here. Like the end result, you can see qubit Q2 holds the state B1 and qubit Q3 holds the state B2. So you apply the particular operation, and B2 is acting as a control state in the initial circuit. Even in the final, after mapping it down, your B2 state is acting as the control, and your B1 state is acting as the target. And over here is the same thing, same story. So easy peasy, everything gets executed. So yeah, so we move down to next. So the next terms is nothing but the gate commutation rules. So these are very helpful when you optimize a particular circuit over here. Like as I said, like when you have two gates back to back, you can get rid of them because they eventually make no sense. They won't make a change they won't change the quantum state. So you can see, like if I have a RX and a C0, I can swap it down, both the same. And if I have two controls, I can swap it down. It won't make a difference. So I have this thing again. Won't make a much difference. So over here, so yeah, so we work it out with the example over here. So C0 and a C0, CX3 and an RX. So yeah, so when we try to map it down in the next one, like we have the layer one which has control one and a control two, and we have a layer two which has control four. So you try it won't actually make a difference if you bring this to this and this over here. So that's what we have actually done over here. So and when you have this thing, so you're trying to just basically mean like if you have two consecutive gates are commutative, which means that they can be exchanged without changing what they compute. So that is the whole difference between this, and this technique is actually very helpful when you optimize your circuit over here. When we try to optimize it, so this is only possible. Like suppose given this part, I have this. I have a swap gate, and then I have an X gate, and I have an RX gate, and a same uh, CNOT operation over here. So my swap gate get converted using this particular part, like this again, and this over here. And with the commutation rule, I can interchange the position of these two gates. So I can bring this to over here and this to over here. So in the next step, when I optimize it, I see these two gates are repeating each other. So I can get rid of them. I can directly put this part and this part in the next part. So this is the application of commutation rules and how they're actually helpful in the optimizing a quantum circuit. Yeah. So yeah. So yeah. So then we have nothing but called dependency graph. So what dependency graph? It actually represents the precedence relation of a gate in a circuit. So if it have like gate U precedes V, that means gate U is being performed before V. So it actually means that there's a path from U to V, that the path exists. So you just like forming the topology of a quantum circuit. So like if I have the first part, like on the left hand side, you can see C1x, CX1, and CX2 has been applied and for a particular qubit. So then you have like the CX3 gate, and which actually means that they can perform in the next particular step. Like they basically tend to mean like there is a communication medium. Like as this gate was performed between two qubits, and so even the next gate can be performed because there is a communication established between these two particular qubits. So that's what basically a dependency graph means. So we just had a walk from the various universal gates family, and then we moved down to the software development kit, like that, which is nothing but like I can say like the communication medium, how do you actually communicate, like how logical qubits they try to communicate with physical qubits. So then we had the functionalities of the quantum compiler, which is nothing but you have a quantum circuit that gets decomposed, all the gates get decomposed into the universal elementary gates, and then with the help of commutation rules, you perform the optimization, and then you try to map down the each logical qubit to the corresponding physical qubit. And then we saw the implementation of a particular example, like how it actually gets implemented given the coupling constraints. And yeah, so we walked around over here and we saw like B3 and B4 are not connected directly with each other. So you bring down the swap gate, you interchange Q3 and Q2. So the states are interchanged. So now you have B3 and B4 directly connected with each other. Then you apply the particular gate. The same circuit flow follows. Then we saw the commutation rules, which actually help a lot when um, performing optimization, because with this you can reduce the number of gate counts. So like when you reduce the number of gate counts, like you increase the fidelity of your state, and which means that you have less noise interference into your quantum quantum chip over there, and you get the best results possible. And then we saw the dependency graph, which just tells like the connectivity, like okay, since this gate has been applied for this two sets of qubits, so even the next gate can be applied. So and it actually tells it more or less it depends upon the coupling graph, like they both are interconnected with each other. So yeah, I conclude now. So, any questions?
Yeah. Nilay,
Yeah.
I have a question. Yeah, that the whole thing you explained is really good. And so we all know that there are few optimization algorithms in normal optimization kind of thing. So is there any optimization algorithm for circuit optimization?
Come again. I didn't get to the last. So, like there are many optimization algorithms for.
Sorry?
I didn't get you. Like there are many like there was an audio problem. Like there are many optimization algorithms for.
Like for normal optimization problem. I mean, for suppose any machine learning type of thing or any other
Yeah,
energy optimization thing. So
yeah.
is there any algorithm for circuit optimization? I mean, the optimizing the number of gates and other things.
Yeah. Okay. I'll show an example. So, like, suppose I have three qubits over here. So, qubit 0, qubit 1, qubit 2, and suppose I'm implementing all the gates using the C0 gate. So, like, I have a C0 over here, and then a C0 over here, and then okay, uh, C0 over here, and I'll say I have a C0 over here. So like in quantum circuits, all gates have their own matrices. Like they all get implemented. They have a particular matrices. So suppose if I have all my gates implemented using the C0 gate, so there is one algorithm. Like I'll just give a touch on it. So like it basically says that they each gate has suppose there are three qubit systems. So you will have a matrix. So okay, so it basically says you have four gates over here, right? So there will be four gates, four matrices. and that will be equal to a resultant matrix. So suppose this is C1, C2, C3, and C4. So this matrix corresponds to C1, this matrix corresponds to C2, and this matrix corresponds to C4. Yeah. And for a traditional C0 gate, if I am not wrong, the uh, the matrix is somewhat this. Yeah, I don't know if I'm correct over here with the matrix part. Like, if
Yeah, the
I
C0
guess,
one is correct. C0 one is
yeah, yeah, this is the traditional C0 matrix, right? Like, yeah. So, and suppose if I have one more qubit over here, so Q3, bear with the drawing. Yeah. So I have a C0 operation over here, and this is nothing but C5. So I will have one more C5 matrix, which, yeah, so this will be the part. So basically, try each K0 operation corresponds to one matrix. So to get the resultant matrix of a particular system, all these K0 operations will get converted into a particular matrix. Like if we're trying to optimize it, so I'll just tell the mathematics behind it. So each C0 operation corresponds to one matrix, and all these matrices will be multiplied to get the resultant matrix, which will represent the resultant state of that particular operation, like of the entire quantum circuit. So I'll just get rid of this. Yeah. So you would have studied, right, like, no, the rows operation and the columns operation in linear algebra. So suppose if I have the C1 matrix, which is nothing but suppose, so this is a 4-qubit system. So my resultant matrix will be nothing but 4 into 4th order. Like this will be the fashion of that particular matrix. So if I have a C1 matrix over here, I'm applying yeah. So over here,
sorry,
this,
Nilay, but the thing, I think the matrix will be of the 16 cross 16 because there are 4 qubits, each have 2 states. So 2 to the
yeah,
power 4 is equal to 16 cross
yeah.
16.
But in the matrix multiplication rule is that if I have my matrix of order m into n, another matrix is of order a into b, these two things should be same, and the resultant matrix would be order of m into b, right? So I'll be multiplying all 4 into 4 matrices, right? So if I multiply 4 into 4 matrix, and so my number of columns of the first matrix is equal to my number of rows in the second matrix. So my resultant matrix will be of order 4 into 4, right? That is the rule of
No,
linear
sorry,
algebra.
I think you are making a mistake because
Okay.
probably the way you multiplied the 4 or the 5 matrices for every C0 gate, and I think that's not the exact way because when you are applying suppose C0 gates between two qubits and the rest of the qubits, on the rest of the qubits there will be identity matrices.
Yeah, no, I get that point. Look, I read an algorithm like for
Okay, okay.
optimizing the circuit. So I'm just
Yeah.
like over there they're represented in this way. So, and I guess it's correct because when you multiply two matrices, this is the two rules, like, and the result, if I have a two matrices of 4 into 4 and 4 into 4 order, like, so this number of rows and columns match, so the resultant matrix will be of order 4 into 4. Like, am I wrong on the rule side? I guess no.
The rule is correct.
You are
Yeah.
right. Okay, fine. Yeah. Continue.
Yeah. So with the rules, I'm just going with the linear algebra, like the matrix multiplication rules. So yeah, so with this, so what this actually says is that I have this this is nothing but q2, and this last row represents q3. So when you're trying to operate or put an operation, C0 operation between q0 to q1, so what I actually do is that I apply a row operation such that my q1 is equal to q0 plus q1. Like, yeah, so my this particular state. So I apply, this is the row operation I apply. So my C1 matrix will be nothing but 1, 0, 0 and 1 1 0 0 and 0 0 0 1 0 0 1 0. So this will be matrix of my C1. So on the similar fashion, all the other gates, like all the like for the C2, C3, C4, all the matrix will be there, and then we multiply it. And after that, we can perform like many Gaussian elimination techniques. Like for the matrices, we have linear decomposition algorithm for the matrix, and even the Gaussian elimination. So then we try to reduce the matrix, and then we work around, and that's how, like, this is the one algorithm, like how do you actually optimize the quantum circuits part. Yeah.
Okay, thank you.
Hello. Can you share this resource for this algorithm for this optimization later?
I'll put it on the Discord channel of
Yeah,
Quantum
sure.
Computing Area. You can get it from there.
Also, what is this optimization technique called?
It's just linear decomposition technique. Like, it's just, I don't remember the title. It's something LDU or I don't really remember the name. Like, I don't remember the name of the research paper title.
Okay.
Yeah, but
Thank you.